All right, welcome everybody. Yeah, there are quite a few people online and a few people in the room, which is wonderful. I'm not going to give a long introduction because Kaylee is one of our own, but I will say that it's always disappointing to me when we have people come join us and we haven't heard about their research yet. So it's always exciting to get these research talks. So I feel like we get another, I don't know, look into the things you're interested in, the things that you know, and I don't know, it inspires fun conversations. So please, everybody, join me in welcoming Kaylee and learning a little bit about what she's been working on the last 5-ish years or so.
Okay, so my dissertation defense, since I just graduated in December, this is semi-fresh, but I've had 2 months to forget it. But this is what I did for the last 5 years, like what Garrick said. So I used the use of nonlinear optics in the characterization of stressed materials. So I'm going to tell you why we did this. And then we used 2 different systems and a lot of different materials. So we used 2 different optical techniques of SHG and SFG, which is some second harmonic generation and some frequency generation. We looked at aluminum, titanium, some polymers. So we'll go into each of those and kind of what we did to them and how they behaved. So why are we doing this? So if you've ever been in a physics class and had to design like a really strong bridge out of newspaper or something like that, you were given this material and you had to make it work for the assignment. That's essentially what we're doing whenever we design anything in the world. When we have aluminum, we want to make a car that's lightweight, so it has good gas mileage, but it still protects us if something happens. They have to use that material or the material they choose, design it in a way that's going to optimize everything they want it to, but also protect us. The way that they test these things, though, can sometimes be destructive. So the image here of this car test is destructive. After they've done this, they can't use that car anymore. That car is not going to be sold. This is great. It still gives us information. It tells us what needs to be changed, what our safety protocols are, or when materials are going to fail, but they can no longer be used. So in the last 20 or so years, non-destructive testing has been a very big field that has been being investigated. There's been many techniques generated that are now used. It can be used to monitor things as is and still be used for their purpose. So some of the techniques that are currently used that are established is there's radiography that deals with essentially an X-ray. This first image in the top corner shows you have a sample, you reflect your radiation at it, you have some detector or film behind it that gives you kind of a map of what might be going on inside of that sample. So you can detect if there's some cracks, some defects, something wrong with that sample. This has limitations. It's not very good with surface defects, and it requires a lot of really expensive equipment, really expensive technicians, expensive facilities, and also you can't just take this out into the field and test your object. You have to bring it to the lab, to that place. So it's not as applicable as they would like it to be. We have magnetic particle inspection that essentially uses a ferromagnetic material, which is one of its limitations. It has to be ferromagnetic. And they generate a magnetic field in that material. And if there's ever a crack or a defect, as you can see in this image here, it will move out of that field that everything else is following, giving an indication that there's a defect. This typically only works when you have surface defects, though, because then you can actually see that field changing. And it also requires you to clean the sample very thoroughly before and after. You have to demagnetize it. It has its own limitations. Obviously, these all have their own advantages. That's why they're used. Dye penetrant testing essentially applies the dye to your sample. That dye then goes into any defects. They clean the dye off, put on an indicator that brings that dye back out. You can see where the defects are and determine if that is a critical damage or not. But this requires a very clean and dry surface, which sometimes we can't have or can take a lot of processing. And it's not very good with coatings and oxidation, which is pretty common when it's actually in use. Two last ones that are really common is ultrasonic testing, which if you've ever gotten an ultrasound to check your kidney or in pregnancy, essentially it's using those sound waves, it bounces back. But if you think about it, if you've ever tried to read that, sitting there getting that exam done, you have no idea what's happening. They're like, oh, look, that's a baby's foot. And you're like, what? So it requires very skilled technicians that can read the information they're getting. This information is not recorded, it's live. So you don't have a record of what might have been damaged, but it does detect, and you can get feedback from any cracks or defects in your sample because the light wouldn't travel, or the sound wouldn't travel as far, but has limitations. Last one that's really common is eddy current testing. This one, they essentially have a coil that's generating a electric field. When they put it close to the sample, it starts to generate its own electric field on the surface of the sample. And you can see that by these rings slightly shown here. When there is some kind of crack, those rings obviously will route around it, changing the way that the magnetic field is being generated in the sample. This is not very good with very thin samples or very thick samples. You kind of have to have the right size. It can only do the surface, and you have to have a skilled technician to read what's going on. So we propose to use spectroscopy as another technique that can either combine with the current ones or eventually could potentially be developed into being a standalone information to tell you what is going on in your materials. So it can get rid of some of these limitations because we could potentially make it a in-field portable system that would not require an expert operation. You could program based on your material whether a signal is good or bad. A simple scan, someone could read red or green, good or bad. And this could allow for lifetime monitoring. So if you can do it in the field, you could keep monitoring and say, okay, no, this is still good. We don't have to take it out. Everything's okay, which means you don't have to pay as much money to get it serviced, to get it replaced. So spectroscopy, for those that don't know it super well, we're gonna think of a scenario first. So if we go out into the ocean and we swim really, really far and there is no land in sight, you only see ocean, you only see sky. Any direction you look around you, you cannot tell where to swim back to shore. But if you look up, there's sky, and if you look down, there's water. So your XY direction, essentially, you can't determine what is X, what is Y, but you can determine what is Z. Z is your up and down. You know that one direction, you can define that. But if you then swim down into the ocean far enough that you don't see light, like this image shows, and you get disoriented because you don't have as much oxygen, you would not know which way to swim. There's people that have done this, they've started swimming and they did not swim up, and you can't define that Z anymore. You're in the bulk of the ocean, everything looks the same, you can't define a direction. So with spectroscopy, the way that nonlinear spectroscopy works, you have to know a direction. So spectroscopy is defined, or the nonlinear spectroscopy we work with, on this equation. So our first term here represents the nonlinear polarization that is generated in your material. And that comes from two input frequencies, giving your double output frequency. And these E's here represent the amplitude, so the amount you're putting in of those electric fields. But the main thing here that boils down to our symmetry is the nonlinear, second order nonlinear susceptibility term. So this term breaks down into third rank tensor that essentially tells us when we can get signal, when we can get that polarization and that 2 omega. It tells us when we can't, what inputs will or will not give us signal, because we need to have a break in symmetry. Essentially here, when you break down all the math of the tensor, if you can't determine a direction, all of those tensors have to equal 0 because X has to equal Y, Z has to equal X. You cannot define anything. So the spectroscopy we work with specifically is spectroscopy at the surface, because you can define metal or polymer versus air, not metal. So we always have a break in symmetry based on the surface, but sometimes depending on the materials we're working with, they might have more susceptibility based on their characteristics to give us more signal that we can then read. So our first system we worked with was second harmonic generation, which follows a similar or a setup to this image shown here, where we have one input light that essentially 2 photons of that light combine to give us a frequency that's doubled. So we start with 532 nanometers in our work and got 266 nanometers as our output SHG signal we were monitoring. So we specifically used an ND-YAG laser that we passed through a wave plate to change that input polarization to give us the most output of our SHG, focused it onto our sample. And because you need a lot of energy and we're only getting signal from our surface, we have to put a lot of green light at our surface to get enough of that 266 to be able to detect it. So light will reflect off of a metal surface, which is what we work with majority of the time. So we have to then put in all these other optics to filter out that light so that it doesn't just swamp our detector, so we can actually see our 266. So we pass through 2 UV mirrors that have about a 95% dump rate of our 532 and reflect our 266. And then we have several UV filters right before our detector, our photomultiplier too. So even after all of that, we still get some green light at our detector. So in our data collection, we would collect however many shots or traces of signal and green, whatever is getting to the detector. And then we would put a glass slide into the line here that would absorb 266. So we would only measure the green light getting to our detector. And in post-processing, we could integrate and subtract them. So over here, our purple is our signal and our background getting to the detector. The green is just the green light getting to our detector. So we could subtract those two and get the true amount of signal we were measuring. So applying this system, the first thing that I worked on was aluminum 2024. So this is an aerospace grade aluminum, and kind of a rationale behind why we care about this one is an example of this AC-130J gunship. So here you see it's inverted. That's not how a plane should look. There was a testing going on after they designed this. Pilot was up in the air. He was about 30,000 feet or 30,000 elevation, and he lost control of the plane. The plane inverted and he dropped like 20,000 in elevation. He was able to regain it, land safely, so everyone was safe, but the ship was not designed to be inverted ever. They did not know the stresses that had happened during that time, so they had to completely throw away and scrap this like $1.3 billion gunship. So having a way that we could detect what's going on in our material if stresses cause it to go past the point of use is very important. So we specifically looked at a very low on the totem pole to get to that point. But we took some aluminum 2024 samples in the shape of this dog bone with this waist, and we put them into a one-time tensile tester. So we essentially had 2 clamps, we clamped it down, and we applied a set extension. When we do this, because of the shape of our sample, the stress localized at the center. So we could take scans with our laser beforehand, see how much second harmonic generation was produced, pull it, stress it mechanically, and then test it afterwards and see if there was a change in the way that our SHG responded. So over here, we also have essentially what's produced mechanically when you pull these samples. You have 2 different regions, and we're going to worry more about the plastic region. So when you're pulling in the elastic region, if you removed that stress, it should go back to the way it originally was. Once it has passed the yield point, it is now in the plastic region, and it is no longer going to go back to the way it was. It's permanently changed. So this doesn't always mean, I guess one of the important things, this does not always mean that there's a crack or micro fractures happening. It could just be plastic deformation that will lead to that eventually. So all those other tests we talked about cannot detect before there's a crack. We believe that we could. So an important thing to know before we show the results of this is that in a material of a metal, there are dislocations that can happen. So a metal is not a single crystal. It's multiple crystal orientations essentially mashed together. And so you have grain boundaries in between those different orientations. Just like in a brick wall, you have your brick that's separate from another brick. It could be a different color, it could be a bigger size. And all that mortar in between it is essentially the grain boundaries. When these crystals are formed, sometimes they can have dislocations or essentially a dislocation, a defect in them that causes a strain on the crystal structure. When a stress is applied, those dislocations can move until they hit a grain boundary. But if they get to the surface, they can cause extrusions and intrusions and give more of a rough surface because they eventually get to that edge of that crystal structure and have an extra atom or less of an atom. So when we do this, we pull our samples. These data points, we show the signal change versus our extension. So the signal change is essentially that signal we took before we pulled it minus what it showed after we pulled it. So when we had our unpulled, there's slight variation just from our laser fluctuations, but it essentially stays at 0. But as we pull our sample, we get past that plastic region, which we define at about 0.5. So this is right on that edge here, this first point. Then we're in the plastic region of deformation. For both a polished and an unpolished sample, we see a significant decrease in signal once it gets more and more damage in that plastic region, soon to being able to crack and fail. The reason we did polished versus unpolished is because unpolished is obviously what we prefer. If we don't have to polish up our nice airplane to test it, then that saves us time, money, resources. So, but it is a little bit more error and fluctuation because the surface is more rough. But because all of those other tests that we talked about that are currently used require a polished and very clean surface, we polished a set of samples to be able to look at another technique and compare. So ultimately we saw a very significant decrease. The further our samples were pulled, the more plastically deformed they were. Why comes up on this next page, because we believe that essentially the SHG signal is coming from the easily polarizable electrons at the surface of the metal. Well, those dislocations we talked about could interrupt that. And there's a test called electron backscatter diffraction that measures the amount of dislocations in the sample. So to kind of give you, focusing on this graph first, an explanation of what this is these are G and D graphs. The red is our grain boundaries. And as you can see, all of the first two, A and B, and the second, C and D, have the same grain boundaries. So we're testing in the same region. The difference between A and B is A is before we have pulled the sample, B is after we have pulled the sample. A is actually a sample that has not been pulled. It's our 0 millimeter to keep a standard. The reason that the coloring changes is because we believe there's a little bit of an annihilation of dislocations happening from the heating that our laser causes, but the amount of change we get in C and D when we pull from no pull to 1.6 millimeters, which is our furthest plastic deformation, that changes way over the small laser annihilation we may be experiencing. So what that shows over here that we can interpolate from those graphs is the blue points are the same from our last graph. These are our polished samples, our SHG signal. Our dislocation density has been inverted to be able to show the correlation. So as it's going down on here, it's actually going up. So our dislocation density, as it increases, our signal decreases. So it kind of matched what we thought, that the more dislocations we have, the less signal we can generate. So we were able to publish this and move on from here, but we wrote, yes.
Can I just ask?
Yeah.
I can't read the scale bars. From
Yes.
The electron though.
They were like 50 micrometers, I
Okay.
believe. It's been a bit.
Mhm.
This was the first project I did.
Okay,
Yeah.
and those were the same samples as you did
The
the
polished.
SHG?
Yep. So the blue data points are polished samples that we had done SHG on. The red points are the dislocation densities taken from those EBSD graphs.
Is your spectroscopy done under air or does it need
Yeah.
vacuum electron? What?
We're just under air. We're just in a room. We're not under vacuum.
But the electron diffraction requires a vacuum.
I don't think it is, because I got trained on it. I don't think it's under vacuum, but it's really expensive equipment. It requires a super clean and polished surface to be able to generate these images.
Thank you.
So the next material we looked at, because we were contacted from our aluminum, was titanium. So essentially, titanium, in this case, we're not doing mechanical deformation. We were actually given samples that had been impacted. So it was still a mechanical deformation. It just wasn't a pulling fashion. So essentially, they were put into an instrument and impacted at an angle until failure. So they were interested in just seeing what our system could see. So we were only given 3 samples that hadn't had anything done to them and 3 samples that had significantly cracked, like shown here, discs of titanium. So when it's impacted though, one thing we did run into with this quick study is you can get a little bit of a dimple on the other side because you're impacting and it's going to push onto that other side. So when we looked at our samples, there was a polished side and an unpolished side of the disc. We wanted to see if that surface finishing affected how our signal responded. But then also, if you think about the disc, one side was experiencing the impact, the other side was not. It was just experiencing it after the fact. So our polished side was the impacted side, and our unpolished side was not. But as we look, our non-impacted samples for our polished side, typically the signal minus this one would go down slightly. The polished side was not very easy to scan. It scattered the light like crazy, the way that they polished it. But our unpolished side always showed that a non-impacted, the impacted significantly decreased in SHG signal. So this was a very quick study. They just wanted us to see what we'd see. So we did see that the finishing matters for the way that we could detect it, but we did see that the SHG did change with the damage when it had a significant amount of damage. We also looked at the difference when we moved away from the crack. So we just tested by the crack for the damage. But because the damage is localized at that crack, we decided to take spots moving about 1 millimeter away, 2 millimeters away from the crack. That's what's being shown here. So at 0, we're right by the crack. As we move over to 10, we're furthest away from the crack. On the polished side, we saw the signal decrease, and on the unpolished side, we saw the signal increase. So this would make sense because they're experiencing opposite types of stress, but on the one side, we see it decrease, and the other side, it increases. Essentially telling us that the further away from the damage, the more it seems like an undamaged sample. So you could potentially have on surface referencing to know if your damage is significant or not. So that one was very small. We worked with the Navy for a naval grade aluminum study that was no longer, we're moving away from mechanical deformation. This was a worry of thermal deformation. So Navy ships are made of aluminum alloy that's doped with magnesium. As you can see in this green image here, it's evenly distributed of aluminum and magnesium. Over time, or if it's exposed to elevated heat, that magnesium moves towards the grain boundaries to alleviate stress. And once it localizes there, if there's enough of it, it forms a secondary phase. So it forms a secondary phase that they call beta phase. When it forms beta phase, they call it sensitized because it now is susceptible to corrosion. The reason they choose aluminum alloy is because it's not susceptible to corrosion, so they can use it out in the salty sea and not have problems with their ships corroding and falling apart. But over time, which is about 20 years for their ships, or if it's near a boiler room or something, they end up starting to have bits and pieces of their ship falling apart, those cracks starting to form. If we think about our brick wall, that mortar is starting to be dissolved and those bricks are falling out. So they can test this and figure out the amount of beta phase that has formed with a destructive test called nitric acid mass loss test, in which they take a chunk of the wall and dissolve it in nitric acid and see how much mass that it loses. Because if you think about taking tiny specks of a brick wall, you're not going to lose that much mass. But if you're dissolving that whole grain boundary, you lose a whole grain. That's a lot more mass loss. So they looked at samples that had been sensitized longer, so heated longer. The samples they sent us were heated for 0, 3, 6.1, and 12.5 days. And they get this ASTM value of their mass loss. So we saw really good results. I'll show you on the next page with our SHG, but it wasn't reproducible with different samples. So we decided to get our own samples that we then did a sensitization that are shown here in the second graph. So we sensitized them in an oven, and then we measured the degree of sensitization by that mass loss. So here, this red arrow shows the equivalent amount of time. So we went past that 12.5 days essentially in heating them. When we look at our SHG signal though, that red arrow is now represented by this red line for our samples. We saw a really good trend with the samples they sent us. It was pretty linear. So we're like, oh, we can detect when something is sensitized so you can replace it without having to dissolve it in nitric acid. Well, when we did it on with our own samples, it was not as promising of a trend, but we did go way past what they had seen. So we didn't go as in detail in this smaller area. And we also, if you've noticed, aluminum 5456 and aluminum 5083 are both naval grade aluminum. They have a slightly different magnesium content. We couldn't get our hands on 5456, so we went with what we could. So the results were pretty mixed, and we didn't get super reproducible things, but I know my lab's looking into getting some 5456 or having another Navy contractor send us samples and information so that we can see if we can get this reproducible again. So the last one on SHG that we're going to talk about is moving away from metals. We worked with a company called Electric Power Research Institute, EPRI, and in their nuclear power plants, they have cabling. That cabling is then covered with a high-pylon cable to protect all their wires and things within it. But like most polymers, like this polymer, over time or at high heats and stuff, it eventually gets brittle and it can start to crack and fires can break out, which we don't want in a nuclear power plant. So they have a destructive test and wanted to see if we could have a non-destructive test. Their non-destructive test is shown here. It's called elongation at break. So just like it sounds, they put it in a tensile tester, they pull it until it breaks. So they took these cables and aged them. So they put them in an oven, added that heat, sped it up, and they'd take it out, pull it, see how fast it was until it broke, basically saying how much life was left. They can't do this in the field and keep using it though. So they sent us samples that they had already sensitized at 4 stages of aging. So each of these points shows an unaged first stage, second stage, third stage, fourth stage. So the red data points are our SHG signal response. The black is their indenter testing, which is another slightly destructive test that they can do. But we wanted to compare specifically to them with these same samples. We found, and in this case, again, to show the correlation, our SHG signal is inverted. So the talk here is 0. So technically we saw as the aging increased, our signal decreased. So we theorized, since this was through another company's things, this could be due to some secondary recrystallization that's happening within the polymer, which is depth dependent, which is where we're looking at. Or like we talked about with the nonlinear susceptibility term, the surface could be changing into a more or less susceptible space group that we get more or less SHG off of. If it was a more susceptible one to start, we got that and the signal surface, but then as we go, we're only getting that signal from the surface symmetry breaking. So to transition over to my last project, we did this on our other system. So I want to explain to you the difference a little bit between the two systems. So we have second harmonic generation we've been talking about, which is shown in this first image here. We essentially have two equal input frequencies that sum together for our output frequency. So we have our one input light giving us the reflected input light and our new signal. Whereas with SFG, it's called sum frequency generation. So it's actually a sum of two different frequencies. We have two different lasers, a visible and an IR, meeting at the same time and location to generate that sum frequency signal that we monitor. The benefit that SFG has, because it's actually more expensive and it's not going to be able to be used as a non-destructive test because it's huge, is it does give us more information. So it gives us vibrations within our samples and can give us a spectrum that has different peaks and valleys that can change when you're interacting with a different surface, different material, based on that material. So the setup is a lot bigger. Like I said, we have one laser that we split the beam to then go through another system of optics to generate our IR. So we have our visible that we have to then take it around a long loop while we're generating our IR signal out of our topaz until we basically essentially have them meet up at our sample mount. And we can control and see different things when we delay when that overlap happens. So we have a delay stage that we can change when that IR and visible light actually meet up, giving us different spectras and more information.
Could you say what are the pulse lengths? Are these nanosecond or picosecond?
I believe it's nanosecond. Yeah. This was my last project, my last year, so I'm not as expert on this, but I believe it is nanosecond. So the last material we looked at with some frequency generation was through the Navy again, but it was a polymer that they used for their explosives. So they dissolve their explosives in this polymer to then use. Well, if anything's happening to their polymer that's changing its properties, they want to know about it. So they wanted us to look into it more. And HTPB, hydroxy-terminated polybutadiene, actually comes as kind of a really viscous, sticky goo. So to make samples and how they cure it, you add IPDI to cure it and put it in an oven for about a week. And we generated and made these molds to give us dog bone shape samples so that we could also do mechanical testing like we had done on our aluminum. So the first thing we looked at was what happens to the sample if it is mechanically deformed. So here we have the spectrum from our SFG. We have the counts. This is all normalized, so it's all to 1. And we have our IR wavelength that is generated, or as our x-axis. So each of these spectrums show before and after, before being blue, red being after a tensile test. So our first one's 0 millimeters, 2, 4, 6, 8, 9. As you can see, looking at this, there's not a very big difference between the before and after. Because these samples were so elastic, once we removed that mechanical stress, it went right back to how it was originally. We even can see that here in the mechanical behavior of it. Nothing is coming to a failure point. We're not getting into any real plastic region. They're all behaving the same. So we'll talk more in a minute about what they're doing with that. But so we were able to determine that it doesn't seem like it's a problem as long as you're not breaking it. It'll go back to how it was. Well, we wanted to look at what happens if it ages or it has thermal stress and how that affects its mechanical behavior. So we add antioxidant to all of our samples. That's what they told us to do. But we wanted to see how big of an impact that was. So we made some samples that did not have antioxidant. Their behavior with SFG was relatively similar. We still have 2 peaks. There's a little bit of noise here. Our laser has had some stability issues. But the biggest thing that we were really fascinated by was their tensile test, their mechanical behavior. Our samples that had antioxidant behaved normally, didn't have a problem, went back to how they were. Our ones without antioxidant, after they had been aged, broke at like 2 millimeters. They barely got anywhere. They completely broke, and we couldn't really test them very easily after that. So we wanted to do a further test into that aging and how that's affecting our samples. So we had standard samples we made that we left them on a desk to naturally age, as everyone does. And as we tested them every 2 weeks for 2 months, we saw that the second and 4th week behaved relatively the same. But once we got to the 6th and 8th week, we see a decrease in the first peak. And then we compared this the same days we tested the same samples that were also artificially aged, that had stayed in an oven being heated. And we saw the exact same trend. We saw that between 2 and 4 weeks to 6 and 8 weeks, there was a decrease in that first signal. So why? This was very recent. They're still working on it now. We think that some preferred orientation may be happening as it ages, or some cross-linking density is changing that's giving us different responses. But that is what we did. So in conclusion, we have 2 projects they're currently working on, our aluminum 5083, the naval grade, and the titanium impact. We actually got some more samples at different extensions and different, or not extensions, impacts, amount of impact, to see if we can actually find a trend besides just damaged and undamaged. And then we've published our 2024 and our cables with aging. And then they're currently working on, it's a 3-year contract with the Navy. They're trying to look at extending. This is our last year. But they're going to continue looking into that aging and why it's happening. But one of the biggest things I wanted to talk about that they're really excited they have going now is because it was not responding with mechanical deformation, because it was so elastic, we actually have devised a system where we can scan it under strain. So seeing what's happening when it's under stress. So they'll have it being pulled while being scanned by the laser. And then they're also going to look at additives, because right now we've been looking at just the polymer, but eventually they want to add the explosives into it. So they've told us that sugar and sand are pretty good simulants of how the explosives interact with the polymer. So they've been looking at sugar. So this is one of the very first looks we had. So the signal obviously changes quite a bit with sugar being added. So don't worry about this. It's not even trustworthy, but they're looking more into that and adding some sugar, seeing what that does to change the spectrum, and obviously still doing the titanium. So I want to thank my family and my lab and all of our funding from the different companies we've worked with and my university, BYU. I also wanted to note that, this group photo was taken like a week before I left, and there's way more girls. When my entire 4 years before, I was the only girl with 5 boys. So this is not normal. So, questions?
Kind of an easy one in that last set of data that you, so before that, so weeks 2 and 4,
Yeah.
and then 6, and you started doing 5.
They are gonna try and do another aging study, especially with adding sugar as well. They want to see like once they have the sugar, how aging changes. We were following kind of another paper we'd seen that they had followed every like 2 weeks for
Yeah.
8.
Yeah, it just seems like right there.
Well-
Is it follow 2 and 4, does it follow 6 and 8, or is it?
So another thing we were doing is we were doing 2 studies at the same time. So every week we were testing a different set. And our laser takes a long time to scan these. So, and the amount of time our undergrads had to help running, it wasn't super doable at the time. But now that we know this happens, they could do a longer study and do it like every week.
Online, Heidi has a question. Heidi, go ahead.
Hi, thanks so much. That was a really great talk, Kaylee. It was really interesting. I have actually lots of questions, but so cut me off at any point. But you know, with the mechanical testing, it looks like you pulled it in 1D till you reach plastic deformation, and so then you could detect the plastic deformation. Do you know if you pulled it differently? Like, for example, if you sheared the material, would you be able to detect the plastic deformation? And then the other thought I had was this crack detection is the sort of size of cracks you can detect and the sort of size of sample that you're looking at to detect any of these things.
So your first question was about the 2024 aluminum, correct?
Yeah, or I mean, with all of them, you did only uniaxial mechanical loading, right? And so I'm just wondering if you did, you know, if you did a different kind of loading, if you would be able to detect that plastic deformation.
So I'm not entirely sure, because the reason we can do it this way and detect it this way is because of the design of our samples. We know exactly where to look for that stress to be able to see before and after change. And like we've said when we published, and I briefly said, this is like the very first of many experiments that would need to happen for this to actually be able to be used. Because like you said, different loading might respond differently. Even like different surface finishings. We looked at unpolished and polished, but there could be different coatings, which optical SHG can look through paint. There's been studies where it looks through paint and gets response. So like coatings wouldn't be a problem, but that's one of the things they would need to look into. I'm not sure, we didn't do any different type of loading.
Okay. And then about the crack size you can detect?
So we weren't detecting any cracks. There was no cracks in the samples yet.
Okay.
That's
so
what
it was
good
just
about
that information you were still detecting.
Yeah, so that's what was good about ours, is there was no cracks yet. We were still being able to see differences in signal. So you could catch it even before any failure was possible.
Okay. And then my other question is like, just about the size of you're looking at, you know, you give the example of like the airplane, right? And so this airplane's got this enormous amount of surface area. And so if you're having to inspect a tiny little area, you know what I mean? So like what area are you looking at to detect?
So we're focused down, I think our spot size was like 2 millimeters, but
Okay.
that's just based on our samples. We could, if there was an instrument designed, obviously it would scan more than 2 millimeters.
Right. Okay, cool. Really great work. Really interesting stuff. I know this non-destructive evaluation is really, really important in engineering and really something a lot of people are looking into in this. So good job.
Thanks.
I totally agree. This is really interesting. I was in particular intrigued by the polymer testing.
Mhm.
And in one of them, you showed us that the undamaged ones, I think, have really large error bars. So when we're looking at the left of those plots,
Here?
yeah. And then
Oh,
I
yeah.
think once it becomes damaged, you go to the right side, right, where the error bars shrink way down.
It's because we get like no signal and there's very little
Okay.
change in the amount of signal we're getting.
Okay, so that's not evidence for your suggestion of recrystallization. It's just a matter of there's so little signal.
There's so little signal, it's not varying very much. Which our error bars are a lot bigger on these sometimes. Well, so on these, I guess I didn't mention that. These are 3 different sets of cables that were made from different manufacturers. So they're all technically Hypalon, but they could have their own manufacturing process. So that's why there's like a different behavior between each of these sets, even though overall we still see that from unaged to age, we have a way significant decrease. There's a little bit of change and difference in the in-between because those samples are made differently.
Nice. Okay. Are there any other questions? All right, let's thank Kaylee one more time. Oh, sorry.
Okay, I just had a couple of quick experimental
Yeah.
questions. Could you go back to your schematic of your experiment at the beginning and then?
Here?
Well, there was an even more primitive version earlier, but no, that's good. That's
Okay.
good. So just to make sure I couldn't
Oh, you're talking about
understand
this
maybe something you said.
Yeah.
You're at a specular angle, right? You're 45 degrees
Mhm.
incident and 45 degrees out.
Yeah.
And if the surface isn't polished, then you'll have a lot of non-specular reflection or scattering of the
Mhm.
light, right? So are your optics such that you're trying to collect all the ultraviolet, all the second harmonic generated light, regardless of the angle it comes out, or are you just with your optics, are you just selecting a specular?
So because we're using a PMT, it's everything that can get in there. We do find that actually polished samples reflect a whole lot more diversely than our unpolished do. So it's a lot easier to get all of the signal that we can from the unpolished samples. For a time, we tried using, well, and there is a lens right here at the front of the stack here to try and focus all of it into the PMT. We tried having a lens right after the sample that was obviously UV transmissive to try and collect it and like narrow it down as much as possible. But it wasn't really changing the amount of signal we were getting or anything like that. And we had to realign everything. So we just left it out after that.
And then something you said about your sun frequency generation spectrum. You have the experimental diagram for that?
Yeah.
You're with your old topaz or
Topaz, yeah.
topaz optical parametric amplifier, right? Is that giving you monochromatic infrared that then you have to scan, like a diffraction or prism element, or is it giving you a broadband where, like in FTIR, you're
Yeah,
scanning?
so it follows very similar to this image. We get this like broad IR, and that's why we delay it with the stage sometimes of where it meets up with the visible.
Right. Okay.
Yeah.
So then you should build up signal to noise in the whole spectrum all the time you're collecting, right?
Yeah.
Okay.
Which we were able to get our system down collection time. That's why I preferred SHG. I could be done in like an hour for collecting data. But as of SFG, when I first got there, the grad student that was finishing up his research came at night to run 2-hour-long scans on a single sample because it took that much to get the noise ratio down and get enough response because there are some issues. But we had a Lithuanian man come out and fix our stuff and make it all fancy again. And we got down to like 1-minute scans, but then it's slowly been declining since. So they're back at about half-an-hour scans when I left for a single sample, single spot.
Thank you. Great job.
Yeah, thank you one more time. A few people online saying thank you as well. Thank you everyone for joining us online.